Rational expressions. In mathematics, the words rational expressions simply means fractions. So in our first example here, we would like to reduce this rational expression to lowest terms. So first, let's recall that if you have a fraction such as 15 over 10, and you're asked to reduce it, what you're going to do is try to identify a common factor. So in this case, 15 is 5 times 3, and 10 is 5 times 2, and then we can cancel the 5's here. Now this is technically because you can rewrite this as 5 over 5 times 3 over 2, and 5 over 5 is 1, so you end up with 1 times 3 over 2, which is 3 over 2. Of course, we don't usually show this step. We normally just cancel those out and go directly to our answer. So then how would we reduce this fraction to lowest terms? Well, first, we have to talk about factoring the numerator and denominator. Now, in this case, this is fairly simple because x squared minus 9, we know, is a difference of two squares, which can be factored fairly easily. And in the bottom, we have x minus 3. Now, you'll notice that in the denominator, I put parentheses around those. You don't have to have these parentheses since there's nothing multiplied, but it doesn't harm anything to have them there. And it makes it a little bit easier, in my opinion, to identify that these two factors here can be canceled. And so this is equal to x plus 3. Now, we need to mention something about restrictions. A lot of rational expressions will have restrictions. In other words, there are numbers that you cannot plug in because it makes the denominator equal to 0. So I think everyone would be able to see here that if I put the number 3 in here, 3 minus 3 would be 0. So 3 is not a number that we can plug into the original expression. Therefore, 3 is not a number that we could plug in to the simplified expression, even though it appears that plugging in 3 here is no problem. Since we're saying this is equivalent to what we started with, we cannot plug the number 3 into our answer. So the answer here is simply x plus 3, but I want to keep in mind that we do maintain the restrictions that we had from the beginning. In the second example here, same thing. We would like to reduce this. So what I'm going to do is factor the denominator, which is a difference of two squares. That one factors fairly easily. Also, the numerator is a pretty simple trinomial to factor. I don't really feel like I have to use a magic X to do this. I know that y squared is y times y. And for 6 and 5, I'm going to use 6 times 1 to give us 6 because negative 6 and positive 1 make negative 5 in the middle. You can check that there. And then you can see very easily that those cancel. And so our final answer is y minus 6 divided by y minus 1. Notice that I can take these parentheses off now because nothing is being multiplied by these any longer. And just to mention the restrictions, y cannot be equal to positive 1 or negative 1, right? I can't plug in positive 1 here. I cannot plug in negative 1 here. And even though this term canceled or this factor canceled, I still have to maintain that restriction, okay? In the next problem, similar thing, reduce to lowest term. So in the numerator, let's talk about factoring. I can pull out a 2 on top, which gives us a cubed minus 8. In the bottom, we can pull out a 4, which will leave us with a squared minus 3a plus 2. And now we just need to factor the rest. Well, a cubed minus 8 is the difference of two cubes, which we talked about in a previous video, but basically you're going to look at that as a cubed minus 2 cubed. And in the denominator, we have a simple trinomial. You could use a magic X if you want, but this one is pretty straightforward. And then the only question is, how do we factor a cubed minus 2 cubed? Well, let's remember that it's a minus 2, and then it's going to be a squared. So we're just squaring this. And then positive 2 times a, which is positive 2a. And then finally, we square the 2 here, which gives us positive 4. And in the denominator, same thing. And then we can cancel a minus 2 and a minus 2. And also, 2 goes into 4 2 times. So our final answer here is a squared plus 2a plus 4 on top, and 2 times a minus 1 in the denominator. And again, if we wanted to talk about restrictions, a cannot be equal to positive 2 or positive 1, because when I go back here, I can see I cannot plug in those numbers. Our next example is a kind of special example because you will run into this quite often. So this is a minus b divided by b minus a. Now, it's very tempting to maybe try to cancel out the a's and cancel out the b's, but remember, these are terms. We cannot cancel terms. We can only cancel factors. So the step to take here is to recall that b minus a is the same as negative b plus a. So I'm getting this by factoring a negative out of here. If I pull a negative out of b, I get negative b left over. And if I pull a negative out of negative a, I get positive a left over. And so this can be rewritten as negative a minus b, right? So now I'm just basically switching these around. And what I can do then, in the denominator here, I can rewrite b minus a as negative a minus b. And then on top, I already have an a minus b, and I'll put that in parentheses. And let's remember that a negative is really like negative 1, and there's a positive 1 here. And so when these cancel out, what I have left over is basically 1 divided by negative 1, which is negative 1. Okay? So anytime you have opposites, so it could be x minus 5 divided by 5 minus x, okay? Or it could be x minus 2 divided by 2 minus x. Or it could be 3 minus x divided by x minus 3. All of these are equal to negative 1, okay? So this is a great shortcut to know. And then in the future, you can just use the shortcut. You don't actually have to go through this step. Next, let's talk about multiplying rational expressions or multiplying fractions. So in this case, we have a simple numerical example, 6 times 7 times 14 over 18. One way to do this is to simply multiply straight across. So 6 times 14 is 84. And 7 times 18 is 126. And this is correct. So again, I'm just multiplying these. But now I have to try to reduce this fraction. So I have to come up with a common factor, okay? This can be kind of challenging. So although you can do this, the better way to do this problem is to reduce these fractions before you multiply. So for example, one thing we could do immediately is we could cancel here because 14 and 18 are both divisible by 2. So 2 goes into 14 7 times, 2 goes into 18 9 times. And now what I have is 6 over 7 times 7 over 9. Now I could multiply these, and this would give me 42 over 63. But then I would still have to reduce this. So is there any other canceling that we could do? Actually, yeah, there's quite a bit left over. We can also cross cancel. So I can cancel the 7 here with the 7 here because 7 goes into 7 one time and 7 goes into 7 one time. And likewise, I can cancel 6 with 9 because 3 goes into 6 2 times and 3 goes into 9 3 times. And so what we end up with here on top is 2 times 1, which is 2, and 1 times 3, which is 3. So we end up getting 2/3. Now, it is true that if you reduce this, you would have also gotten to 2/3, but it's just more difficult to reduce after you multiply. So we always want to reduce our fractions before we multiply. Here we are multiplying a couple of fractions that only have monomials. Now, monomial means that there are no pluses or minuses, right? So we just have 8x cubed divided by 27y to the 8th, then times 9y cubed divided by 12x squared. So the principles are the same. We can cross-cancel things. It can be a little bit tricky when you have monomials like this. So I like to say, leave yourself plenty of room so that you can see your cancellations very easily. So for example, x squared will cancel out 2 of these 3 x's. So we will still have an x left over there, right? And that just comes from x cubed divided by x squared. You can subtract exponents, right? So, 3 minus 2 here is 1. So we just have the 1x left over on top. Same thing with the y to the 8th and the y cubed. So think of it as these 3 y's right here. So that's y times y times y. Will cancel out 3 out of the 8 y's that you had down there. So you'll have 5 y's left over. A way to kind of visualize this, and of course you don't want to have to write all this down because this would just be very time consuming, but those 3 y's on top cancel out 3 of the y's in the bottom, and you can see that you have 5 y's multiplied together left over. And then of course 9 goes into 27 3 times, 4 goes into 8 2 times, and 4 goes into 12 3 times. But do you see how it's really messy, right? It's kind of hard to see what's left over on top. Well, we have a 2, but remember we also have an x right there. So on top, it looks like we have 2x, everything else canceled. In the bottom, we have 3y to the 5th times 3, and that is 9y to the 5th. And that is reduced. So in this next problem, we are multiplying these. This looks like a lot of work, but basically what we need to do is factor all 4 of these polynomials. Now, I won't get into all the factoring. I'll just show you the steps one by one here. So when you factor by taking out the greatest common factor here, and then using the magic X on these two, you should get the following. Okay, so you can pause this and double check all those if you want. And then I could start canceling, but I want to point out that there is one little bit of factoring left to do down here, right? When I pull the 2 out of here, I get y squared minus 1. This is the difference of 2 squares, so that can be factored. All right, and then now we can start canceling out. So I have a y minus 2 up here, which cross cancels with the y minus 2 down here. I have a y minus 3 canceling out here. Y plus 1 canceling out here. And then 2 and 2 cancel. And then we just have to make sure that we see everything that is left. So in the numerator, it would appear that all we have left is a y. And in the denominator, all we have left is y minus 1. And this is our answer, okay? Now be careful. Don't do something silly like cancel these y's here. You cannot do that because these are terms, not factors. Next example is very similar, except that now it is division. So how do we divide? Well, first we change our division to multiplication, and then we flip the second fraction. That is the definition of division. So you can see I took that step here. Now what I need to do is factor all of these. Now these are multivariable polynomials, but they're not that hard to factor. X squared minus y squared is a difference of 2 squares. So it factors into x minus y times x plus y. Down below here, this one's also pretty simple to factor. We know that x times x is x squared. We know that y times y is y squared. All right, we need a negative and a negative here to get negative 2xy. You can double check that. Over here in the bottom, we have a sum of 2 cubes. So that is going to factor as follows. See the previous video on that. And then up on top, we have x cubed minus x squared times y. We can pull out an x squared, and we have x minus y left over. Okay, so once I have all those factored, now I just need to start canceling out common factors. X minus y, another x minus y here and here, x plus y here and here, and it appears that what we have left over is x squared on top and x squared minus xy plus y squared in the denominator. So in this example here, we are multiplying 4x squared minus 36 times 12 over 4x plus 12. So first of all, let's just write this as a fraction. So 4x squared minus 36 over 1 multiplied by 12 over 4x plus 12. And now before I start canceling things, make sure you factor first. So 4x squared minus 36, we can pull out a 4, and we have x squared minus 9 left over. Oops, this is multiplication. And then I have 12, and then in the denominator down here, I can pull out a 4, and that gives us x plus 3 left over. And then x squared minus 9 can factor into x minus 3 times x plus 3. And the rest is good. And now I can cancel. I can cross cancel x plus 3 with x plus 3. And then here I have a choice. I can cancel 4 goes into 12 3 times, so I'd put a 3 up here. Or I could simply cross cancel the 4 with the 4 over there. I think I'm going to do that. That's a little bit more straightforward. And then what we have left over on top is x minus 3 multiplied by 12, so that's 12 times x minus 3. And in the bottom, we just have 1, right, because everything canceled. So my final answer is 12 times x minus 3, or you could write this as 12x minus 36. Both of these would be acceptable answers. Now, I am kind of ignoring the restrictions here. In the beginning, when we factored right here, we can see that x cannot be equal to negative 3. So I'll just mention that, but I won't keep on mentioning the restrictions. You just need to be aware that restrictions are always there. Back to multiplication here, we have 3 times x minus 2 times x minus 1 multiplied by 5 over x squared minus 3x plus 2. Again, the thing to do here is to just simply make a fraction out of the first expression there. And then after doing that, you can factor the denominator here. And then we're just back to good old cross-canceling. And you can see all we have left over in the end is 3 times 5, which is 15. Adding rational expressions is a little bit more challenging. Remember, to add rational expressions or to add fractions, you must have a common denominator. So in our first example here, you can see that we do indeed have a common denominator. Both of these fractions have x squared minus 1 in the denominator. So our answer is going to have the same denominator, and then all we have to do is add the numerators. So that will be x plus 1. So this is our answer, except that we might be able to reduce, and in this case we can. X squared minus 1 is a difference of 2 squares. And when we reduce here, what we have left over in the end is a 1 on top and x minus 1 in the denominator. Okay, so our final answer here is 1 over x minus 1. Sometimes when you add fractions, you don't have a common denominator and you have to get a common denominator. So let's take a numerical example like 3/14 plus 7 over 30. Now, when you're doing numbers, a lot of times what you'll do is you'll just factor those numbers. So 3 over 14 can be thought of as 3 over 2 times 7, right? 2 times 7 is 14. And then 7 over 30, 30 factors into 2 times 15, and 15 factors into 3 times 5. So it's 2 times 3 times 5. And once we see the prime factors for those numbers, we know what we have to multiply to make these denominators the same. So you can see they already both have a 2 in the denominator. But this denominator has a 7 and this one does not. So to make the second fraction have the same denominator as the first fraction, I know I have to multiply the top and the bottom by 7. But then this fraction over here has 3 and 5 as well. This one doesn't. So I need to multiply this one by 3 and 5 in the bottom and also on top to have a common denominator. So you see now our common denominator is 2 times 3 times 5 times 7. And that is 6 times 35, which is 210, okay? So this fraction here becomes 3 times 5 times 3, which is 45 over 210. And the second fraction becomes 7 times 7, which is 49 over 210. Our common denominator comes into the answer, and then we simply we add 45 plus 49, which is 94. Okay, so our answer is 94 over 210. And then now the question is, can we reduce this? And the answer is yes, because both of these numbers are divisible by 2. 2 goes into 94 47 times, and 2 goes into 210 105 times. So our final answer here should be 47 over 105, as long as there are no other common factors, which there aren't. So now, how do we add fractions that have variable denominators that are not the same? Well, the first step is you need to factor each of these denominators. So this first fraction is going to be written as negative 2 over x minus 3 times x plus 1 plus, and then we have 3 over x squared minus 9 is x minus 3 times x plus 3. So we can see that they both have x minus 3 in the denominator. So that part of the denominator is in common already. But this fraction has x plus 1, and this one does not. And the other fraction has x plus 3, and this one does not. So we need to multiply each of the fractions by what they are missing from the other denominator. And when we do this, it's actually better to leave ourselves a little bit more space. So let me rewrite this. Okay, and now like we said, in the first fraction, we are missing the x plus 3. So I am going to multiply by x plus 3 to the numerator and denominator. And in the second fraction, we are missing x plus 1. So let's multiply by x plus 1 to the numerator and denominator. Now the next step is really important. In the denominator, I am simply going to write down all of the factors they have in common, and I'm going to do that for both. So you can see now they have a common denominator. Now in the numerator, I am actually going to multiply these together. Okay, so what I'm going to do here is negative 2 times x and negative 2 times 3. And that's negative 2x minus 6. And then the same thing for the other one. 3 times x, 3 times 1 is 3x plus 1. 3x plus 3. There we go. Now, the reason we're doing that is because, remember, in your final answer, you are going to keep the common denominator. So we want that to be in its factored form. But in the numerator, you are going to add these together. Okay, so what I have in the numerator is negative 2x minus 6 plus 3x plus 3. And now when I add those, in the numerator, I get negative 2x plus 3x is x, and then negative 6 plus 3 is minus 3. And then the denominator just carries over. And then I ask the final question, can that be reduced? And the answer here is yes, because if I think of that as a whole factor, those will cancel out. And so my final answer here is 1 over x plus 1 times x plus 3. So it's a procedure, and you'll get better at it as you practice. Now subtraction works the exact same way. So in this problem, I have x plus 4 over 2 times x plus 10 can be factored into 2 times the quantity x plus 5 minus. And then we have, let's leave a little more room, 5 over x squared minus 25 is the difference of 2 squares. Now we need to multiply by whatever is missing. So in the first fraction, we need a factor of x minus 5. okay? Because we can see we have that here. In the second fraction, we need a 2. I'm going to multiply the top and bottom by 2. So I'll just squeeze that in right here. And I'm doing that because we have a 2 right there. They both already had x plus 5, so that was good. Now we're going to rewrite these two fractions with their common denominators in factored form. And then I'm going to multiply out the numerators. So here it's very simple. 2 times 5 is 10. But here I need to FOIL, right? I need to multiply this out. And that's going to be x squared minus x minus 20. Now our final answer, we're going to keep our common denominator. By the way, I should point out that when you write your common denominators, it doesn't matter if the factors are in a different order as long as they're all the same, okay? So I have 2 times x plus 5 times x minus 5. And in the numerator, we have x squared minus x minus 20 minus 10. Well, negative 20 minus 10 is negative 30. So that's going to become x squared minus x minus 30. And this is our answer unless we can reduce it. And it turns out here that we can reduce it because the numerator factors into x minus 6 times x plus 5. And the denominator is the same. And then we can cancel the common factor. So our final answer here is x minus 6 over 2 times the quantity, x minus 5. The last topic for this video is something called complex fractions. Complex fractions are when you have smaller fractions inside of a larger fraction. So you can see here we have one large fraction and then 4 smaller fractions within the large fraction. The easiest way to simplify these is to identify the least common denominator of all the small fractions. So in this case, that's going to be x times y. And then I'm simply going to multiply the numerator by x times y and the denominator times x times y. And that means that all 4 of these get multiplied by x times y. So we have xy multiplied by 1 over x plus xy multiplied by 1 over y. And in the denominator, we have xy multiplied by 1 over x minus xy multiplied by 1 over y. And the thought process is xy is xy over 1, okay? And then we're just doing cross-canceling. So here I can cancel x with x. Here I can cancel y with y. Down here, same idea. And what you have left over when you focus on each of these 4, even though it gets a little messy, but you can see that the only thing left over right here is y times 1, which is y, plus x times 1 here is x. And in the denominator, in a similar way, we have y minus x. And that's our answer. Now be careful here because it's tempting to want to cancel something with this, but these do not cancel. And our final example, another complex fraction. Notice that the least common denominator here is x squared. So what I'm going to do is just take this fraction and multiply the top and bottom by x squared. And so that's what it looks like. And then I'm going to distribute. So I'm going to multiply x squared times 1, which of course is just x squared. And then x squared times 4 over x squared. Now think about what happens when you multiply these. The x squared here is going to cancel with the x squared there. And so we're just going to have minus 4 left over. In the denominator, same thing. X squared times 1 is x squared. Then we have x squared times 1 over x. Now let's think about that. X squared times 1 over x. This x is going to cancel one of those x's and just give us x. So that's going to be minus x. And then finally, minus 6, right? Because when we multiply here, the x squared cancels completely. Now I'm just going to factor the numerator, factor the denominator, and then you can see we can cancel out the common factor. And our final answer here is x minus 2 over x minus 3. And that concludes this video lesson.